Another recursive algorithm, and basically you're going to go until you hit a null spot, and you're going to print the left and then print the right. But in the middle, you're actually writing the info for each of the nodes. It's kind of bizarre. So let's see what happens. So we have that tree up there. Maybe I should do it with a smaller tree. What do you think? Let's make our tree just a little smaller. Okay? So, well, maybe I should do this. Okay. So we come in with our tree that's pointing to the 10, okay? If the tree is not null, then we're going to print the left of the tree. So we're going to go to the left. Okay? Now since we're calling print left tree, we're not even doing anything else yet. We're going to come right back up here. Okay? If the tree is not null, which it's not because it's the 5, we're going to print left tree. So now we're going to call it with the 3, right? Do I need to write this down? Or are you getting it? Okay, it's not null. We're going to print left 3, the left of the tree. Now it's null, right? So it is null. So we, okay, so I should probably write these things down. So let's start with the beginning. So the first thing we did was we print, and I'm just going to put the 10, and it's the rest of the tree from the 10, okay? And then we called print with the 5. And then we called print with the 3, and then we called print with a null, right? Is that what happened? Okay, so print null, we don't do anything, so it is null, so this now goes away and we come back to the print of 3. Okay, we come in here, it's not null. We are done with all the print lefts. So we're going to write, we come out of here. We called it from here and it returns to here. So the next thing we do is write info. So we're going to write the 3. And then we're going to print anything to the right of that. Is there anything to the right of the 3? No. So we don't do anything. Well, it comes up, so it prints it's a null, and it just comes back to here. Okay? Then we're done with that. We come to the print 5, and then we write the info, which is 5. Is there anything to the right of the 5? Yes. So now it's going to print 7. Okay. Is it null? No. So we're going to print left. And what's to the left of 7? Null. Okay. So that null comes back. And the okay, so we had done, we're going to write the info of the 5 first. I mean, we already wrote the info of 5. So we're going to write the info of the 7. And then that one goes away. Okay, now we're done with the 5, so that one goes away. Okay? This is really confusing. But guess what happens? Guess how it ends up being printed? In ascending order. Okay? So we did the whole left tree. At this point, we're going to write 10. And then we're going to go print its right tree. Well, its right tree is 42, and then null, and then we write 42. So it's kind of a mind-boggling algorithm. But basically what it does is it travels. So let's put our other tree back. What did we have? We had 69, 83, 23, right? 5,
12 and 18. 12.
12. What? We'll
12 is
put
not-
12 here. And
12 is off
Oh, yeah. 12 is off of the 23, and the 18 is here. Okay, so this is what it does. It comes up here, and it goes to print the tree. But it's first going to traverse all the way down the left side of it. So we're going to go to the left until we hit an end node, okay? We're going to write that one. Then we're going to write the one that we're on. And then we're going to go and write everything to the right. We're going to go all the way to the right, okay? Then we come up here to this one, and then we're going to go to the right. So we come to here, but we have to go to the left first. Okay, the next one to the left is the 12. And, well, there's nothing, and then 12, and then 18. Okay, and then 23, and then 42. And then all the way down to the right, we come to this one and we write all of it to the left, but there's nothing there, so we're going to write that one, and then it's one to the right. So it goes to the left, the node to the right, to the left, the node, the right. Okay?
Right.
Kind of crazy, but basically it ends up putting them in order if your tree is done correctly. Okay? And then there's this one, it figures out the length of the tree, and basically it's another crazy one. It figures out the length of the left of the tree plus the length of the right of the tree plus 1. Why is it plus 1?
Because you
have the
mentioned the root.
You have that root. So you go to the left and it figures out the length, and you go to the right and it figures out the length, and then you have to take in that one. But for each one, you're going to the left, and for each one, you're going to the right. So that's binary search trees. Okay? The only other thing in this chapter then are graphs. Okay? So if you look at page 261, you see an example of a graph. And they use this whole big example of airlines, okay? And you basically just traverse where the arrows go. You can go wherever an arrow is pointing. Okay, so I think there's a question that I have you answer, and it might say what's the shortest path or whatever, but I'm not going to go deeply into graphs. Okay? I think you can all sort of follow along. So if we wanted to get from Austin to Washington, how would we get there? Is there more than one way to get there? Okay, so what's one way we can get there?
From Boston to Houston.
To Houston.
And Houston to Atlanta.
Okay.
And then Atlanta to Washington.
Okay. And it tells you how many miles are there, so we could add up the miles. Okay, and then what's another way we can go?
Austin to Dallas.
Uh-huh.
Dallas to,
Denver.
Dallas to Denver,
yeah.
Denver to Atlanta.
Denver to Atlanta,
And Atlanta to
and
Washington.
Atlanta to Washington. And we could add up those miles, and we can see which is the shortest. We can see which is the shortest way, and which is the way with less stops, or more stops. Okay. So it's not that difficult. There's an algorithm here that we're not even going to go look through. A searching a graph. And the depth first search and the breadth first search, and we're not even going to worry about it, okay? Except that I think there's just one, I think I have you answer a question, but it's basically doing what I just did with you. Okay? And then, the book talks about subprograms, and a subprogram is just a program that calls another. It's a function that calls a function. Okay? So when we have one function, and it's not calling itself, it's calling something else. So maybe, I have a function that calculates an average, but in that function I call a function called sum. Okay, so sum is a sub-program or sub-function of the average function. Okay, I don't like the term sub-program. To me, that isn't a good term, because it's not really a sub-program. It's a function in a program. So I would probably use the name function, and I think on the test I put I say sub-program, I put function in parentheses, I put like sub-program. Okay, so, but basically it's when one function calls another function, not calling itself, because what's that called when you call itself? Recursive. Okay. Okay. So chapter 9 talks about, so that's everything in chapter 8. Okay, because the next thing is the parameter passing the Bowery method. Passing by value, passing by reference, right? What's passing by value?
Immediate.
What?
Immediate.
Immediate.
Passing by value means
That's right. What?
Passes the value.
Copy that.
It copies the value, okay? And passing by reference,
Passes the address.
it passes the address. Okay, so passing by value is immediate, and passing by address,
It's
by
direct.
reference is direct. Okay? Okay, so, maybe I'll sit, because I don't think I need to write anything on the board. Or maybe I do. No, I don't know. Okay, I'll stand. Okay, so, this is talking about, this chapter 9 is talking about object-oriented versus procedural design, or what we call top-down design. Okay? And what's the difference between these paradigms? And what's a paradigm? Anyone know what a paradigm is? It's like more like a model. Okay? It's a model of, or a pattern. How you're going to do something. It's a model. It's the way that something is supposed to work in, okay, in the paradigm. So when I first learned to program, it was all top-down. Okay, programming languages like Fortran, Pascal, C, those are all top-down procedural programs. So you have functions that call functions that call functions, and it all just kind of works its way down. Okay, and you pass values around, pass parameters, and we had a lot of global variables that we would use, and it was just one program that went, so you break it down smaller and smaller and smaller parts, and it would just go straight down. Okay? And then along came object-oriented programming languages, so that would be Java, C++, Python. Okay, these are object-oriented. And that is a whole different way of looking at the world. It's a whole different paradigm. And when you learn to program in one paradigm, it's a little difficult to switch to another paradigm, let me tell you. Okay, it took me quite a while to figure out truly what how the object-oriented paradigm works. But now we tend to teach students the object-oriented paradigm first. And that's how they learn to think, so it's much easier. Okay? Because it turns out that object-oriented programming is better. Now, all object-oriented programming also has some procedural programming in it. Okay? Because you are going to have functions, you are going to have kind of a top-down way that you figure out your algorithms. But what objects do is you have these independent things that we call objects. It's a compartment. And in that compartment is the data and everything you can do to the data for that object. And then the objects interact with each other. But each object is responsible for its own data manipulation. Okay? So, I have a table object, and the table has four, this table has 4 legs, so I might have something, how many legs does it have? How tall is it? How wide? You know, what's the dimensions of the table? Does it have anything on it? I can put things on it, take things off. All of this, these are all, that's the data and the functions of what I can do to this table. I can lower it, I can raise, you know, if the legs can be lowered or raised. Okay? And then I have a chair. It's a different object that has its own data. It has a size, it has a number of legs, it has all the same kinds of things. But I can take that chair and put it on the table. Okay? And now they are interacting. So if I have a function to put something on the table and then it has to know that it has something on the table, if I put that chair on the table, it has to know that there's a chair object on the table. Okay? So that's what object-oriented programming is about in a nutshell. Okay? Let's see. Okay, so say I wanted to define a person. So what kind of things would a person, what kind of data would a person have? Name, age, height, weight, gender, what?
Blood type.
Blood type, that's great. This is all data that a person would have, okay? And I would be able to initialize all the values for that person, you know, put all the values in. I'd be able to get the values for the person, so I'd be able to say, the name of the person is John Smith. I can assign that. And then if I wanted to see what the name of the person is, I could say, get the name of the person, and it would give me back John Smith. Okay, so those are some of the functions that this person object would have to have. I need functions to set all the values, I need functions to get all the values. And then I might need a function to add a year to their age. Okay, I might need a function to change their address. Okay? Maybe they cut their hair, or they changed the color of their hair, or something like that. I need functions to do all these things to manipulate the data that I'm going to need for this person. Okay. There are things in, well, I'll talk about that at the end. Well, 3 essential things that every object-oriented programming language has are, let me erase the board. The first one is called encapsulation. Encapsulation is where you hide the details of how something works. So remember how we talked about a car, and then we don't have to know how a car works in order to, like, you don't have to know how the engine works in order to drive a car. And we need to know the things about driving, but we don't have to know how that car is running. Okay? And so hiding those details of how something works is called encapsulation. Okay? Separating the data from the actions, basically. So it's hiding the details. So with a car, I do tell you some things. I say, push on this thing, it's called the gas pedal, and that'll make you go. Push on this thing, it's called the brake, and that will make you stop. Okay, turn this thing, it's called the steering wheel, and that will tell you which direction you're going. So I give you those, I do tell you that much about how to drive the car, but I don't tell you anything about how it's working. Okay? So that's encapsulation. And then the next thing that object-oriented languages have is something called inheritance. Okay? And that would be one object can inherit everything from another object. Okay? And it's so objects can inherit data and functions, which are called methods. Okay, so an object has data and functions that we call methods that manipulate the data, okay? Inherit the data and methods from other. Okay, so we have a person. Person has all those things that we decided they had: a name, an age, height, a weight, hair color, whatever, an eye color, a gender, okay? And then we have something called a student. Well, a student is a person, right? And so usually we say is for inheritance. So first of all, a student is a person, but then a student has extra stuff. Might have an ID number, a GPA, a major. Okay? So student can inherit everything from person. So student also has all of this that person has, and we don't have to redefine it, because it's already defined here in person. So student can first inherit person, and then you can add on the other things that a student needs specifically. Okay? And the last thing that every object-oriented language has is called polymorphism, which is different objects can have methods or functions that are called the same thing but do something specific. They work specifically for that object. Okay. So how do they? So functions can have functions with the same name or methods with the same name will work specifically. Methods. Well, let's see. Two objects, how about that? Two objects can have a method with the same name, but it works specifically for that object. Okay? So it might be something as simple as writing out the values in the object. Writing them out. So for a person, I would write name, age, height, I'd have stuff in there to write name, write age, write height, whatever. Right? But in a student, I want to, and I call that function write, or print, or something. I'm going to have this, I can use the same name of the function, print or write, same exact name, and it will work specifically now for a student. Okay, that's what polymorphism is. And so you usually see these things in a greater than, less than. So you make a greater than function for two objects to be able to compare, or equal to. You want to see if two objects are equal. And you might have people that have an equal as one defined one way, and shapes that have an equal defined as a different way. But they can still have the same name, equal. Okay, you can't have that in top-down design. A function has to have a unique name, can do its thing, it's unique. Okay, that's polymorphism. So, back. Okay. So when we talked about programming languages like C and